Hello everyone, and welcome to a new episode of Advent of Code 2016. This one's going to be a bit of a hybrid episode, in the sense that I've already looked at this problem, problem 12 here. Are these little notifications showing up in the video? They're not, right? Yeah, okay. Getting some notifications from an unrelated program. Just wanted to make sure that it wasn't looking silly for you guys. So I've already done part of this problem, and I want to present that part to you in review, and then finish up the rest of it live, or well, live as a recording gets. But I'll go over the problem briefly. So blah blah blah. Who cares? You're supposed to implement a computer that handles this this simple assembly language that has 4 instructions. It has 4 registers: A, B, C, and D. And these commands can be, well, some of the commands have to be registers. Some of them can be either registers or literal numbers. I mean, it's just a pretty straightforward simple specification for a simple assembly language, right? You know, the computer starts at the top. It executes each instruction one at a time and does what it says. You can add 1 to a register. You can decrease a register by 1. Or you can conditionally jump based on whether a value is 0 or not. And you can set a value, move a value, either a literal or a register, into another register. So let's see. Let's look first at our input here. It's just a pretty small program. Maybe you could look at it and figure out something clever and cool that it's doing, but it's not totally obvious to me. And what about our source code? Well, this is the part that like I said, I've done some of this, and I want to walk you guys through what I've done so far, because I've actually done it a number of different ways that I want to show the differences between. The first thing is modeling of our domain. So we have a class for each of the instruction types. They're sort of, at the moment, just acting like smart tuples again, or you might say verbose tuples. Kind of dumb tuples that we had to rebuild some of the tuple functionality into, right, like the constructor and so on. But they have names, you know. And so, in fact, we can Python source.py input, and we've implemented the repr function. Well, actually, hang on. This was a different version that I wanted to show off. So we've implemented. This is what the code I'm currently want to show off does. It parses into these. Actually, this is evidence that I made a mistake in one of the other versions I want to show off. Anyway, so the idea is we parse the input, and we get then I say, okay, now let's print the domain objects modeling the input, and what we get back is something that looks a lot like the input, but we haven't just implemented cat, right? We've turned stuff into Python-friendly objects, and then shown that those objects represent the domain. And to make that clear, I indicated, oh, C is a register, and -2 is a literal, right? So that's the only thing we're getting right now out of having parsed it, but we'll get more later. And so we also have these 2 classes for what kind of argument it is. Rather than just storing the string A or the number 5 or whatever, we store an object, which is saying it's either a literal argument or it's a register-based argument. Fine. And we have this class computer that we're going to do something with later, but that we haven't done yet. So what I want to show off first is a RegEx-based method. We've been doing all of our parsing with regular expressions, and a lot of people use regular expressions for parsing, and it's fine, it's great. So the thing that I forgot was that I actually return register of x, right? So yeah, this is more what I meant. Oops, interesting. So okay, I've made some mistakes here. So let's look at the regex based approach before I show you any of the others. Basically, we have a function that parses a line, and since we have to, well, okay, let's ignore this inner function for a moment and start here. What do? Well, we have a regex for like, does the thing match copy? And like, well, it's pretty clear how to match a number and like how to match a letter. And here it's like, okay, it's the first argument is either optionally a negative sign followed by some digits, or it's A through D. And then the second one is just A through D. And fine, if that matches, then we pull out the first group and the second group, and like we make a copy instruction out of it. If that didn't work, now we try another regex. Inc is a pretty simple regex, and we just return the first group, basically, right? Now it turns out that what I forgot is that I have to wrap inc of register of m.group, and here register of m.group, and then we actually get the output that I wanted, which, oops, still not right. Interesting. Copy. Ah, yes, this needs to be a register as well, right? And now we've parsed it all into proper domain objects. So this accidentally demonstrates something that I wanted to demonstrate, sort of like, oh, just imagine problems like this arising. But this very repetitive approach, we have like a constant amount of work for each different instruction that we might want to parse. And it's not a small constant, right? It's actually kind of like, the regex, they're all pretty simple. Not that hard to write. But there's repetition, right? I have this instruction, this sub-regex here, which is like how to parse a thing that's either a number or a register. And I have the same thing appearing here and here, oops, here. And if like we maybe someday needed to change it so that actually registers can be multiple lines long, multiple letters long, I would have to change it in 5 or 6 places. Actually, numbers can be floating point. I'd have to change that in a bunch of places, right? And also, there's just a bunch of fiddly details with like, okay, great, I've matched it and I've parsed it as a string. Now, what exactly do I do with each of the arguments, each of the groups? You have to remember exactly how to wrap them up into domain objects of like copy. And oh, so we never did get back to this. It's just like, it takes the result of one of these matches and then checks to see, was it the first half that matched or the second half? And if so, wraps it in a literal and parses the int. Otherwise, wraps it in a register. Okay, so like, this all is a possible thing. It's not a huge problem for a small thing. And in fact, this was pretty quick to write. And reasonably quick to debug, even if you include the time that I thought I had already debugged it and then demoed it on camera and realized I had forgotten an important step of like wrapping things in domain objects instead of just returning them as strings. So, fine. That's a regex-based approach. But I want to show you another thing that you could do. And I've done it. I've chosen to show it off first in Haskell because there's this. If you've never heard of parser combinators, they're like really cool. A really cool way of composing together, combining small parsers into large parsers. In a way that composes well, that scales well. Whereas with regexes, you basically just have like each regex is an island unto itself, and you have to build the whole thing by in isolation of everything else. And like you can try to concatenate together regex strings, but it's just like real hard, and you shouldn't do it. It's gonna make your life sad. So parser combinators are a way of building objects in your language and combining them together into a parser in a way that you can reuse small bits and pieces the way you would. If you wanted to write a 1,000-line function, you wouldn't write it all at once. You'd write a couple 100-line functions and combine them together. And you'd be like, geez, those 100-line functions need to be smaller. So you write some smaller functions and compose those together. In the same way, parser combinators, so that's sort of like function combination, right? So parser combinators let you do the same thing with a parser. And I'm demonstrating this in Haskell because Haskell is, I don't know if it's where the idea of parser combinators first arose, but it's certainly where it first gained popularity. Well, I say certainly, I don't know. I'm no computer historian. That's where I learned about it. And certainly parsec is like the dominant force in parser combinators. Every language out there has an implementation of parsec, and parsec came from Haskell. And they're all like varying degrees of good, but like parsec is this thing that's really great. Parsing stuff is a breeze in Haskell, and so I wanted to show you guys this approach first before I show you using the same approach in Python. First of all, something I've mentioned, I believe, before is this is all of the domain modeling we had to do in Haskell. An argument is either a register, which is a character, or a literal, which is an int. Or I should say, rather than which is, containing. It's either a register containing a character or a literal containing an int. And like deriving show is like basically, oh, and please implement repr for me. Or the Haskell version of repr, which is called show. So these objects will print themselves. Oops, there's some noise. And the other thing that we want is an instruction, which is either a copy composed of 2 args, or an inc composed of 1 arg, or a dec of 1 arg, or a jump non-zero composed of 2 args. And please implement show on this for me as well. So that's all the modeling. Let's compare that to Python, where we have everything from line 5 to line 41. Okay, so we've saved some lines. We've certainly made it more terse. And we really only had to tell Haskell the absolute minimum of domain-oriented stuff. We didn't have to build stuff in terms of like the language and re-implement a bunch of... Anyway, it's nice. I like Haskell's algebraic data types. They're a cornerstone of the language, and everything that there is focused around making these things easy to work with. And they're easy to define as well. Okay, so then we get to the parsing, which is this, basically. Now, how many lines? Out of curiosity, if we were counting lines, how many is this? This is 13 lines, and the Python RegEx parsing code is, similar, right? It's like from line 63 to 81. It's like 18 lines, right? 19. It's pretty similar. I wouldn't pick nits about the difference there. But what's important is that well, there's a few important things, right? You also might point out that like here, we're basically implementing parse int, which like is something you're going to be able to reuse a lot of times. In Python, it's a built-in. In Haskell, we had to implement it. It does exist, but like not in a format that is convenient to use here, so I just implemented it. So in a sense, all of our domain-specific parsing is this. Pretty good, right? Like 9 lines, including 2 white space lines. Very dense. And again, containing almost only stuff that is specific to our domain. Not a lot of like repetitive nonsense that you just sort of have to type in every time you write a program. I'm not going to try to explain what all of this does in great detail because, it's not going to make a ton of sense without knowing Haskell. But I can explain some of this, which is basically like these operations with like angle brackets in them are generally like parse the thing on the left and then parse the thing on the right. There are various flavors of what those are, whatever. And this one is a little bit different. It's parse the thing on the left or parse the thing on the right. So basically, we have this instruction parser, which is parse, well, okay. We have a function named bytecode, which takes the name of an instruction and a constructor to call to make a value a domain object out of it. So we implemented that right here. And it's just like parse the string containing this name, and then also parse an argument, and like call the function on the result, basically. This is simplifying, but that's the idea. And so then our instruction is just, well, try parsing the bytecode copy. If you succeed, then also parse an additional argument for it. Otherwise, try parsing bytecode inc, and that's it. Otherwise, try parsing the bytecode dec. Otherwise, try parsing the bytecode jnz, and if you do, parse another argument for it. So we've avoided repeating the logic about how you parse arguments, right? This is basically like, you know, try parsing an int, and if you succeed, then call literal on it. Otherwise, parse any character at all. We could have been more specific and said parse a letter A through D, and then call register on it. And furthermore, before you do any of that, throw away a space character. So, whereas in the Python version, we had to have a function that was like how to parse a thing, which is great. We had a function and we only wrote, you know, the code for that function once, but the regex for parsing it, we wrote 3 times, right? Here, here, here. And if we had more instructions, you can see how this would quickly balloon out of control. And if there are any changes to the specification or anything you forget, you have to change it in a bunch of places. So parser combinators are great because basically combinators for anything are great. Functions are in a way like combinators of logic. I mean, probably there is a thing called a logical combinator, and I don't know what it is. But functions are sort of combinators for writing programs in general. And by using parser combinators, you can make your parsers into functions that compose just as well as ordinary functions do. Very exciting. So with that said, what if we tried to use parser combinators in Python? There's nothing, I mean, there are some things special about Haskell, but in general, you know, languages are Turing complete, and Python has lambdas, which is like a big part of what makes parsec work. It doesn't really have monadic whatever, but we don't need a lot of that for this. So there's a lot about the language Haskell that makes parsec particularly well suited, and makes it a little hard to port to other languages. But you can get a lot of the way there. So in Python, there is a library called parsec, inspired by parsec in Haskell. And here, I've written a parser combinator-based parser in Python for this same input format. And so we're doing something very similar to what we did in Haskell, defining some small parsers like parse value, which is, okay, parsec, I need you to choose, i.e. try the first thing, and then if it fails, try the second thing, either a letter, and then once you've succeeded, map register onto that. Just like mapping over a list. Like if you have a list of things, you can map a function over the list, and you get the result of like calling f on each thing in the list. You can, in a sense, map over a parser and say, okay, if I have a parser whose value is 10, please give me back a parser whose value is 20 by mapping double over it or whatever. But here what we're mapping over is the function register, saying, okay, I have a parser that contains within it a letter, and I want it to instead call the function register on that letter and then contain the result. So that's sort of how this stuff all works, is you have parsers and you work with the stuff inside of them. There's, again, this is kind of high-level glossing over stuff because there are some concepts involved in parsec that I don't know the right way to explain in Python. Maybe there's some built-in that's a lot like this that I just don't know about. But it's in a way, it's a lot like mapping over a list. You can map over a parser by pretending the parser has a value inside of it, even though that's really not exactly what's going on. Anyway, so to parse a value, you choose either a letter and then map register, or this little regex here for matching a number. And then we do this map thing over it. We say, okay, yes, but also call int on it, and then also call literal on that. And we have a value parser. And we only need to use that once, because we write this function parse args, or a parser, parse args, which is basically separated is this function in parsec, which says, okay, well, I've got a parser that I want to run a bunch of times, parse value, and there's going to be some stuff in between them, parsec space, that I want you to throw away. It's not interesting. And we want between 1 and 2 occurrences of that, of the value. And then I have this little map here, which is like, given a string, what's the right Python constructor to call? And so now there's a new parser, parse an instruction's name, which is like, call parsec.choice a bunch of times, choose either copy or inc or dec or j and z, and basically a parser that accepts the string that we're thinking of and returns as a result the function that we're thinking of. We're sort of building as a list comprehension over instructions.items, this map here. We're reducing this map into a parser, so that we have a parser that returns that has as a value inside of it a function. That's sort of a weird concept. What is it? We've talked about having a value inside of a parser and mapping a function over it, but you can actually, functions are values. You can put those inside of parsers. Why not? And then this is the only thing that's a little bit like, I wouldn't say convoluted, but it's a bit nested of like what is going on. And you have to get to bind. Bind is like a thing that takes some work to get your brain around, and I'm not going to try to introduce it here, but basically, I say that to parse a line, I first parse an instruction, and then bind, which is kind of like do the first thing and then the second thing. I bind to apply args. And the most interesting thing involved in apply args is like you parse a space and then throw it away. So remember, we did like the same thing in Haskell. We had this space and throw it away. In Python, it's parse this space and then throw it away, and then parse this thing, parse args, which we wrote earlier, and then map over the args this lambda that calls the constructor that we have already had inside of the instruction name parser. So it's all a bit involved. And they're all perfectly reasonable approaches, and there are, I'm sure, even more reasonable approaches. You can write, a recursive descent parser by hand in Python for this. It's not too hard if you have taken a class on parsing or read a paper about, or even probably an article on the web or something. Recursive descent is sort of like a fairly straightforward approach to parsing things in a top-down fashion using like functions. And I guess it requires some formal knowledge. Sometimes, I don't really know what stuff is actually hard. There are definitely things that are hard for me, but sometimes stuff that it's like, oh yeah, I remember learning that freshman year of college or whatever, or I guess mostly like senior year for this comp sci stuff. But there are plenty of people who didn't go to college and still do computer stuff for a living, and I don't exactly know what... I take it for granted, right, the education. Like, oh yeah, it's recursive descent, it's real easy. It may require more formal knowledge than I remember in order for it to seem easy. But my point is, parsing regexes is fine for small things like this. But even if you don't really know what's going on with parser combinators, I think it's good to know that, for larger parsing problems, there are tools out there that you can look up for combining together small problems into a large problem, or small solutions into a large solution. And actually, let's just real quick, let's go run the Haskell program as well, right? Stack run ghc source app this. Does this still work? Oh, do I have to download a bunch of stuff? The last time I ran this was on a different computer. In fact, I didn't write this on this computer, so I don't know. Maybe stack run ghc is not going to work out so great. It might take a while. Yeah, it's downloading a bunch of stuff to install, but eventually this will display some stuff. We'll get back to this. So now that we've implemented our parser, it shouldn't actually be too much more work to implement running the program. The main thing that we need is we need to finish modeling this computer. And I think it's actually fine for just it to be basically like pass. No, I think we'll want a constructor for it. Definite of self to be self and program to be self.program equals program. Self, and it wants registers as well. Registers, self.registers equals registers. Self.IP, the instruction pointer equals 0. Maybe we would want that passed in as an argument. I don't know. But so the idea is that each of these instructions is going to have an apply method which takes as an argument a computer and modifies the computer's state accordingly. So let's do copy. That should be pretty easy. Def apply self computer to be let's see. We're copying. The other thing is these two arguments are going to need a way to know about a computer as well. So let's write def eval self computer. Actually, let's pass it the registers even to be return self.val. So for literals, we don't care about the registers; we throw them away. But def eval of self and registers to be return registers of self.reg. Okay, great. So now we have that, and we can use it inside of inc and dec and all that stuff. So we'll just say to apply ourselves. Is the Haskell thing done yet? Compiler version mismatched. Okay, well, bleh. Can I just change that real quick in my Cabal file? I compiled this on a computer with a newer version of Haskell, and the project file that it defined apparently wants a newer version of Haskell. I don't know what to do about that. I don't really know my way around the Haskell ecosystem very well. I just sort of know what's going on inside of files, source files. But in terms of the architecture for building things, I haven't done a lot. Anything more complicated than Advent of Code 2015, I have not done. All right, but you guys take my word for it. I ran it on a different computer, and it can parse the instructions and then print them back out in a Haskell-friendly looking way by using show. Okay, so how do we apply a copy? Well, we say regs equals computer.registers, and we say regs of self.dest equals self.source.eval of registers, right? We evaluate our argument in the context of some registers, and then we write the value into the target register. Easy enough. I guess we were putting repr at the bottom. I don't know what the style thing to do is in Python, but it sort of feels natural to me to put repr at the bottom. Def apply self computer for an inc is regs equals computer dot registers regs of self dot reg equals regs of self dot reg plus 1. And we'll just grab this and implement the same thing for dec, but with minus. J and Z is a little more interesting. We sort of have to decide at what point do we change the instruction pointer. We could do it at the end of each instruction. It feels a little bit weird for me to do that. You could do it after every instruction. But then it's like a little bit weird for jump, right? So I think what we're going to do is have jump just jump by 1 less than the offset and assume that the instruction pointer is always incremented. Or jump 1 lower than the offset. And then we'll just automatically increment at the end of every step. So how about J and Z? We have to define apply here. Def apply self computer to be. Let's see. Do I need the registers? I don't need to save them. So I'm just going to say if self dot reg dot, actually I will want the registers. No, because offset is a constant. What does it say? In our test input, do we have any non-constant offsets? No, they're all constants. Okay. So if self.reg.eval of computers.computer.registers equals 0, then computer.ip equals computer.ip plus offset self.offset minus 1. So we're counting on the automatic increment here. And I think that's all, right? That's all of our instructions. They all have very simple eval or apply functions. Wait, self.reg is a string. Oh, it's called reg, but it should just be arg, right? Yeah, I called it reg because I thought that it had to be a register that we were comparing against, but it doesn't. And likewise, we actually, when we call J and Z, we're parsing it as an arg. So offset will be actually not a number, but a literal. So we'll call eval of it on the registers anyway. That way you could pass a variable offset. Why not? So let's just say regs equals computer.registers. So arg.eval of regs equals 0. Oh, I forgot. That's all. We were already doing all that. We don't need the registers for anything else. Oh, because I wanted to eval self.offset is the thing. Even though it's always going to be a literal, we should actually call eval of regs. This way, if it were ever not a literal, it would just work. So that's kind of nice. Okay, great. So now we need to just write. So what does the specification say? After executing, when you move past the last instruction, the program halts. Okay. So let's just give our computer a def exec function, right? It's just like run until you run out of inputs. And this is where like the big loop is going to happen and all that stuff. So let's see. I guess we have while self.ip is less than len of self.program. Self.program of self.ip dot, so that's now looking up an instruction object, dot apply to self. That's what it wants? Yes, self. Great. And that's like it. I think that's all. That's pretty cool. So let's go down to main here and just like sort of assume it's going to work. Maybe it will. Who knows? Does it compile? No. Def exec. Apparently that's a reserved name. Run program. Yes. Now it compiles. Okay. So in main, we'll say CPU equals a computer of what? What order does computer want its arguments in? It wants the program first and then the registers. Okay. Well, let's actually say instructions. So I happen to know what part 2 is going to be. So I may be a little bit. I saw someone else's solution in a different language, and part 2 is like just run the same program, but with the instructions not with the registers initializing something other than 0. So I know we'll need the same instructions for both things. So what we'll do is just say instructions equals parse line. What do they call it? Line parser? No, parse line dot parse of line dot rstrip for line in sys dot stdin. Regs equals k maps to 0 for k in range, no, in ABCD. CPU equals computer of instr regs, instrs regs, CPU dot exec, run program, and then what exactly am I supposed to look up here? What value is in A? Print CPU dot regs of A. Okay, well, that seems exciting. What's going to happen? Global name registers, we forgot a self somewhere. Figures. I think. Yes. No, that's right. I guess I should just ask the... Oh, this one's supposed to be regs. All right, we figured it out. I should have just looked at what line number the error was on. Uh-oh. This is running for a while. I thought it would be done pretty quick. Is this evidence that we have a problem? It could just be a program that takes a while to run. How exactly could we introspect whether it's getting any work done? I mean, we could just print like every time an instruction runs, this is the instruction that we're running. But that's going to start swamping our terminal with output, and it won't really clarify how much progress we're making. Oh, I know what's wrong. We forgot to increment the instruction counter. Self.ip equal IP equals self.ip plus 1. Key error of regd. Where? Line 23. I'm sure we're here. Inc. Register. We have to look up the register's name because reg here is actually an arg. It's a register object, so we got to look up .reg on it. That's maybe a little dubious. Maybe I should have. But it's just sort of more convenient to have registers have have everything have arg objects instead of have some things be literal ints, some things be literal strings, and some things be these objects. So we'll say r equals self.reg. A little bit dubious there, but r, yeah. So actually, hang on. Do we? In our constructor, we could take that out, but I'd rather not. And likewise in dec, we'll say r equals self.reg. Again, I'm not totally convinced that this is the cleanest way of doing things. But okay, sure. How about now? Computer instance has no attribute regs. Oh, is it called registers? All right, well, the good news is it ran real fast this time. And indeed, we could actually just look at regs, this here. It's the same map, right? But, okay, 3? Really? That answer is too low. That's exciting. I thought what we were doing was honestly pretty straightforward. We discovered there were some problems. Unknown the magnitude of those problems, but we just tried running our program against a sample input, or against our actual input, and it didn't work. And then we took a break, and we're back. And I believe I suggested, well, let's try running it on the sample program and see how we do. And the answer we're supposed to get is 42. But we get like a radically different answer. Let me... wait, no, is that the right button? There we go. Now you guys can see. I tried running the program on the sample, and the result that it yields is 0. So that's obviously quite wrong. The first thing to note is that I realized it's a jump not 0, and we have implemented instead a like jump 0, basically, right? Here. Evaluate the argument in the context of the register. But check if it is 0. Well, that's not right. We want to check if it's not 0, then we do a jump. So that's fine, but that shouldn't be enough to fix the sample program, right? Like, we get 1. So I think something is wrong with copy as well. Yeah, I see. So the problem is that is the same as we had in Inc and Dec. We're setting the value not at the character A, but the value in the map where the key is the register object map of character A, basically. So we need to look at self.dest.reg, basically, right? And now we get 42. Okay. Now when we run it on the real input, how does it do? We get a much larger number. That seems quite plausible. And indeed, it is the right answer. Okay, well, this is maybe going to be a pretty short episode, huh? Maybe I'll edit them together. So, part two. Oh, right. The register C needs to be initialized to 1 first. Okay, well, that's easy enough for us to fix. The first thing is, why did we have this at all? Let's just inline it, right? Like so. Actually, stop. Let's commit. Git add. I don't know, we have some changes. What did we change? We implemented the program, basically, since last time we committed. Day 12, part 1. Implemented program. Okay, now we can inline this into here. And then let's say CPU 1 equals this, and CPU 2 equals computer insters. And is there like a good way to get a map like this but with one value changed? I don't think there is. Really? You kind of have to like define it. Base regs equals this, I guess. So base regs dot copy, is that a thing? I forget. Python copy map, copy dict, grumble, copy dict, please. Okay, sounds like dict.copy is actually a thing that exists and is a shallow copy, which is fine. That's all we need. Yes. Okay. Great. And then let's write base regs of C equals 1. And I guess we'll just call this regs since it's not actually just the base regs. We're reusing it. Regs dot copy just to be a little CPU2.run program. So let's I don't know, split it up like this. CPU1, 2. And now, of course, we don't actually need CPU1's value anymore, but as I've said numerous times, I like to, where possible, have my program output, where convenient anyway, have my program output both solutions rather than just one, so that I can see how small of a change I needed to make to accommodate the new requirements rather than to replace the old requirements. I think it's a nice way to think about, like, as a program changes over time, when you're writing a program like for a real program that matters for work or whatever other project you have, when you get new requirements, you generally need to like accommodate them within the scope of how the thing is originally set up and not like just throw away the old version. Why is this taking so long? I thought it was going faster than that. I thought we were finishing pretty quick. What's wrong here? Huh. Oh, we're running both programs now. That's what's wrong. I meant it would have been reasonable to do this, but I didn't. And so it gets all the way to the end before it prints either output. Okay, that's fine. That's the right answer. Okay, we are done with day 12. Yeah, this was just 7 minutes. I'll just tack it on to the end of the last episode. Okay, well, I sort of already said goodbye about 8 minutes ago. But at the time, I didn't realize that we were going to be done so quick. So here we are. Goodbye again. Thanks for watching. Hope you enjoyed, and I'll see you next time.